Hello, my name is Stephen Bornheimer, and I will be presenting a presentation on flight, a look at hot air balloons and airplane flight. This presentation is intended for a high school audience. To be more specific, it's intended for a 9th, 10th grade audience with backgrounds in basic weather, algebra, and basic physical science or understanding of atoms. So let's begin. These are the basic concepts we'll be discussing in this presentation. We'll be talking about lift, more so the force of lift. A little bit on propulsion will be mentioned, but more so fluid properties, what is a fluid and what are its characteristics, density, and Bernoulli's Principle. The first unmanned flight was made in 1783 by French scientist de Rosière. And it was made in a hot air balloon. At first, they had the hot air balloon tethered to the ground, but as they began to really look at it and they were comfortable with it, they let the hot air balloon go. And the first recorded flight was over 500 feet off the ground. This kind of flight was, if you look, was 100 years ago or so, or a couple hundred years ago. And since then, we've made many strides in understanding how flight works, but we will kind of review some of those in this presentation. Alright, so hot air versus cold air. It might seem kind of funny to be talking about air, but ultimately it is really kind of crucial to look at some of the properties of air for this presentation. First of all, it's important to understand that air is a fluid. That means that it can flow relatively freely. It's not like a solid, which has a rigid structure, maybe it's a lattice structure or a crystalline structure, but fluids have the ability to take the shape of their container. And this particular property of being able to move about, especially with gases, because not only do they take the shape of their container, in some kind of like water can, but they can also take the volume of their container, which means they entirely fill it, and that's an important characteristic that we're going to explore or look at. Okay, so in looking at a hot air balloon, the first thing we notice is that it's called hot air for a reason, and that is that we heat it up. And when we heat it up, that means that we're increasing the temperature. So we know that the air is made up of tiny little particles and atoms of hydrogen and oxygen molecules. There's a little bit of argon in there, a lot of nitrogen, so on and so forth, CO2, water vapor, etc. And in order to kind of look at what would happen to the volume of that gas when heated, we want to go ahead and just take a look at the combined gas law. We can think of gas or air as being kind of an ideal gas. So in that being the case, we see that here's the combined gas law, and we see that if you heat up the gas, the temperature 2, which is this value right here, is going to be greater than temperature 1, meaning that when you heat up the gas, the final temperature is going to be greater than the initial temperature. Okay, so the 1s refer to initial values, the 2s refer to final values. In looking at this version of the equation here, we see that pressure 1 is going to be equal to pressure 2. We're going to talk about why that is in just a moment. But basically, that value becomes a big giant 1 because they are equal to one another. So if you have an increase in temperature and you're looking at the volume of the gas, basically what this means is that this fraction here is greater than 1, and when you multiply it by V1, you're going to get a larger value. This can kind of allude to the fact that when you heat a gas, it's going to expand, and it's going to take up a larger volume. So, this is the diagram of a hot air balloon. We call this very large area the envelope, and here's the parachute valve. Here's the parachute cord that opens the valve. Okay, and the skirt down here is kind of a big opening as well. So when you heat all of that hot air, okay, when you heat it all up inside here, okay, and it starts to expand, it's going to want to go somewhere. And if the parachute valve is not open, that hot air is going to escape out through the bottom. Now that leads to a couple of different things. First of all, it means that there's actually going to be less air inside the envelope. Okay, and that less air means that there's going to be less mass inside the envelope. Okay, and that's going to be crucial. So if we take a microscopic look or even an atomic look at what's happening here, as that air leaves, it's going to leave fewer particles inside the balloon. Now, the pressure is exactly the same. Okay, because these particles are moving faster, they're hitting with more force, they're actually providing the same amount of pressure, so we don't see the balloon get really big and we don't see it shrink. The pressure on both sides is equal. However, we do see that there are fewer particles in here, which means that you have less mass. And this decrease in mass, in conjunction with the volume of the balloon staying relatively constant. Now, when I say the volume of the gas expanded, that's the volume of the gas, and that gas was pushed out. But the volume of the balloon itself, the envelope, is going to stay relatively the same. And so if you have a constant volume and a decrease in mass, that's going to be really crucial looking at why the air balloon, the hot air balloon itself, will have flight. Okay, so we think about density. Density equals mass. Density equals mass over volume. If you decrease the mass and keep the volume the same, you're going to decrease the density. It's a direct proportion between density and mass. So if you remove air from the envelope because, in essence, you are heating it up and it's expanding, you're decreasing the density. And when you decrease the density, the hot air balloon will begin to rise because, in essence, it's going to kind of float or rise above anything that is more dense around it. If you think about the density tower here, we see that like the ping pong balls sitting on top. These are all fluids in the density tower. Okay, lamp oil, rubbing alcohol, vegetable oil, water. But they separate out according to their density. Objects like the cherry tomato stop because it is more dense than dish soap but less dense than milk. And so it kind of keeps its spot here. So the hot air balloon, if we can think about this density tower as being the atmosphere and the hot air balloon's down here, as it becomes less dense, it's going to rise up through the tower, okay, or rise up through the air until it comes to a point where it's got the same density as the air around it. And this can happen because we can monitor the amount of hot air in a balloon. We can cool it off by releasing hot air and letting in cooler air. We also, as we rise through the atmosphere, the air becomes thinner, which means that the density of the air is going to decrease. So actually, a balloon eventually would get to a point where the density inside and outside would be relatively the same. Okay, so that's what causes a hot air balloon to rise. This is a really good video, and I would encourage you guys to watch it if you wanted to introduce or kind of recover the idea of density. Okay, so hot air balloons basically float because air inside them, which is when heated, is less dense than the air surrounding the balloon. And this is a great little animation. It's in the regular presentation, which will be posted on the discussion board. Okay, now let's talk about the aspect of flight or lift when it comes to airplane wings. This is a really great lesson when you're kind of talking through buoyancy or anything dealing with flight or fluids, or aerodynamics or the design of cars or sailboats, because this idea of lift or air passing around an object, aerodynamics in essence, is applicable across the board for many different fields, many different subjects, etc. So let's go ahead and get started. Alright, have you ever felt the wind blow? Wind is the result of moving air from high pressure systems to low pressure systems. In a high pressure system like the one that we see here, the air, is kind of flowing downward and it's flowing towards a low pressure system, which then gets sucked up and forms the cyclone, basically another term for a thunderhead. Now we see that this high pressure is going towards low pressure, and this high pressure versus low pressure is important for us because it really does it really does play an important role in moving air. That's why when it's sunny outside, there's not a whole lot of wind. When it's really stormy outside, there's a lot of wind. You may be wondering why in a hot air balloon then, if we're talking high pressure and low pressure, does the air not escape? And the essence is because, like we said, the pressure on the inside and outside is the same. But when it comes to airplane wings, okay, like let's say you're an airplane wing like this, when air is passing over it, there's going to be a difference in pressure. Okay, and we see, just like in the wind example, when you have differences in pressure, you have air traveling from high to low. We're going to see some of the same things happen when looking at airplane wings. Okay, so we oftentimes associate low pressure with windiness and high pressure with non-existent winds. Okay, so when we talk about low pressure, oftentimes is going to deal with this idea that things are moving very quickly, whereas high pressure things are moving, very or less quickly. So we have faster winds oftentimes in low pressure systems. So we kind of want to think of low as being fast and high as being not as fast. So we'll just say slower. That doesn't necessarily mean that it's not fast, just it's slower than low pressure systems. Okay. Now, instead of like a wind or big, huge air masses, which could cover half the United States, like when we talk about the weather, when we're talking about an airplane wing, we're talking about a surface. Okay. So imagine for a moment you have a surface like this one right here, and on one side you have a high pressure, and on the other side you have low pressure. Okay. Well, in order to get balance, there's going to be a lot more. These particles are going to want to push on this to the left. They're going to want to push. They're going to provide more force, okay, because of the higher pressure, and so they're going to want to go to the low pressure side, okay. And if you think about them balancing or canceling each other out, these would cancel out, and these would cancel out. But ultimately, the high pressure is going to provide a very large force in this direction. And that's the direction that is going to ultimately provide a net force, which in this case would be to the left. Okay, now if you recall, pressure is actually what we call collision. So every time one of these little particles collides with the surface, it's exerting pressure. And when we look at the pressure of a system, we're kind of taking the sum of all of those collisions. So the more particles you have, the more collisions you have, and therefore the greater the pressure. Okay, so this idea of it should be high. This idea of this should be high pressure, exerting a force against low pressure, was brought to the attention of the scientific community by Swedish scientist Daniel Bernoulli in 1738. Now, that date is kind of significant because it means that Bernoulli was exploring these concepts of pressure well before man ever even had an unmanned flight. Okay, because remember, the first unmanned flight was in 1783. Okay, which was almost 50 years later. Okay, so Bernoulli was looking at these differences in pressure much earlier on, and the implications were not quite fully understood until at least with hot air balloons. But even so, Bernoulli's principle doesn't even really apply to hot air balloons so much as it applies to flight, which was the Wright brothers, who really had the first successful airplanes. So these ideas of Bernoulli principle and lift weren't really optimized or weren't really thought through or made applicable to flight until many years later. Okay, so if you imagine for a moment that the sail is an airplane wing, okay, it kind of looks like an airplane wing. As air travels along the bottom, okay, it's traveling normal, okay, it's trying to get from point A to point B. However, air traveling across the top of the wing has to kind of go in a kind of kind of not necessarily in a straight line, but kind of in an arc around the wing. And that it's still trying to get from A to B, so it's still trying to cover the same distance. Or it's still trying to get from point A to B or have the same displacement. However, it's going to go a further distance. However, both the blue D and the red D have to happen in the same amount of time. So if you think about it, D here is larger than D here. And if we convert that into kind of like velocity, where we look at the distance over time, or at least speed in this case, being a scalar quantity, we can see that because D over T is a greater distance in the same amount of time, it's going to be a faster speed, which means that the air moving across the top of the wing, so up here, is going faster. And if it's going faster, okay, it has lower pressure. So fast, again, means low pressure. Down here, the air is going slower, and therefore it's going to have a higher pressure. And because of that higher pressure, kind of like what we were talking about on one of the previous slides, there's going to be a greater force pushing up against that low pressure, and thus we get this concept called lift. And that's how an airplane wing works. It's the movement of air at different speeds across what they call airfoil or envelope here. And as we move across it, these differences in speeds create differences in pressure. And thanks to Bernoulli and recognizing this as a kind of a constant thing in nature, we've been able to kind of use it to create lift in an airplane. Now, we can use different shapes for airplane wings. Just to kind of give you the quick run through here. If you are just kind of cruising along, you want your airplane wing to be as flat as possible. You want to minimize lift. You want to make sure the air is very similar. And that's what we see happening up here. However, if you want a little bit more lift, you're going to kind of extend your flap out and put a little bit more tilt to the wing. That means the air has to travel just slightly further, meaning that you're going to have a little bit more lift. However, notice that we're keeping the streamline effect here. We're going for speed, we're going for little drag, so both of these would be good for like cruising and taking off. Now this one creates absolutely the most lift possible, okay, because the air has to travel much further in this example. However, it's also dipping down, which means there's going to be a lot of drag right in here, and that drag is going to slow the airplane down. So this would be really good if you're trying to make a light landing and you're trying to slow the aircraft down while also creating enough lift to just gently touch down on the ground. This last example really is, we're not going for any lift, where the air is coming through here, the air is coming through here, there's really no curvature happening, the air is escaping, but there's also this flap back here that's causing drag, and this means that we're just trying to purely slow the aircraft down, and this is really for braking purposes, is how this works. Okay, lastly, just to give a little perspective, this is a great photo. You can see here that the air is kind of condensed, and we can kind of see the cloud of it as it passes over the airplane wing. Alright, so this is just kind of showing you the path of the air as it travels over the wing like so. Alright, this was my presentation. The bibliography, and you can kind of scroll through it or pause or look. All materials were either obtained with permission or obtained as per the user agreement of the website which they were obtained, meaning that all these are for non-commercial use and for personal use only. So anyway, if you have any questions, you can email me. Otherwise, thank you for watching my presentation.